Hello, everyone. Welcome back. Um, so I sent you all your progress reports. You should have received them on whatever email you have currently on CUNY first. So if you have any questions about the progress reports, I'll be more than happy. We could talk about them now if you want. The progress report itself is hang on one second. Just needed to clean up my screen here a little bit. There's a lot of junk. So the progress report is a format that just comes out right out of my gradebook. The reason I do that is I want you all to see what your current grade is in my gradebook as of right now. I do that because sometimes I make a mistake in copying the grade from one place to another. We found one situation like that so far where I had to fix the grade. So please take a look at your progress report. Tell me if I made some mistake in grading your assignments, copying the grade from Blackboard or from the book or whatever, or from Mimir. If I made a mistake, I'd be happy to fix it. The one thing about the Mimir grade, the Zybook grade for your participation activities is that you have to be aware that the participation activity, I grade it, I pick out your grade from the book based on when the activity was due. Okay, so for example, your chapter 6 is due, I believe, this Sunday to complete chapter 6. I will look at the grade as of Sunday at 11:59 p.m. If you go back later on and you finish the activity, whatever your grade was on Sunday is whatever the grade will be. Even if you finish your assignment later on, it is whatever the grade was at 11:59 p.m. on Sunday. I believe that's the 18th. So just be aware of that. So you might look at your Zybook and say, oh, I got a higher grade on this than you gave me, but it's not really what it is right now. It's what it was at the time when the deadline was. So I copy the grades out of the textbook, I copy the grades out of the Mimir, I copy the grades out of Blackboard, and I put them all into my grade book. I produced this progress report for you guys so you can take a look to see what your grade currently is. Just for the record, 60 is passing. Okay, 60 is a D. Anything below 60 is not passing. Any questions before we start talking about anything that we want to talk about here today? Continuing with binary search trees, but anybody have any questions that you'd like to talk about?
Yeah, I had a quick question. It was regarding to the progress report.
Sure.
So like, I took a brief look at it. I just want to, I guess, understand how would I figure my letter grade from all the information given? Like, how would I calculate that? Or is there a way to?
The letter grades are easy. 50 to 60 is a D. 70, no, 60 to 70 is a D. 70 to 73 is a C minus. 73 to 77 is a C. 77 to 80 is a C plus. 80 to 83 is a B minus. 83 to 87 is a B. 87 and up to 90 is a B plus. 90 to 93 is a B minus. 93 to 97, 93 to 100 is an A. Okay, it's whatever. If you look at the Lehman website for how number grades convert to letter grades, I think it's on the Lehman website that says that's the setup. Okay.
You said 87 to 93 is a B minus?
No, B minus is 80 to 83.
Mm-hmm.
E is 83 to 87. 87 to 90 is an B plus. 90 to 93 is an A minus. 93 and above is an A.
Got it. Thank you.
Okay. So that's the thing to sort of like, if you'd like to talk about your grade, if there's some personal issue that has to do with your grade, please go ahead and schedule an office hours appointment so we can talk about it. Okay. Anybody else?
Professor,
Yes, Eric.
can you talk a little bit more about the hash table classes in homework 5?
The hash table class.
Yes.
Okay, what is it that you would like to know?
Like, for example, how you put the list onto the hash table, like in the add element, right? How
Okay,
would
so
you, like, what is the function to decide in what bucket will go?
okay, so let me share my screen with you, and we'll talk about it. Okay, so you can assume you can see my screen.
And also a little bit about the iterator too, because I'm not sure how the iterator will work in this case.
Okay, so let's take a look. Okay, the way you create the hash table, okay, is when before you call the constructor for the hash table, you create an array. You yourself create an array, okay, which are the list of buckets. It's the buckets that you have, okay? And each one of these buckets here is a linked list, okay? Each one of these buckets, so there's n buckets. This is bucket 0, 1, 2, 3, boom, 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 all the way to n, whatever n is. All right, so you in your driver will create this array that contains linked lists. Basically, it's an array of linked lists of the proper type, okay?
Quick
Yeah, go ahead.
quick question while you're at it. So we initialize right away all the linked lists for the bucket. So we only initialize it when we're trying to introduce an element in that bucket.
No, you create the array of linked lists to create the hash table.
Oh, okay.
So before you create the hash table, you create the array of linked lists. Okay? We're good?
Yes.
Okay, so far so good. So now the next thing is, now somebody gives you an item to put, an element to put into the table. Okay? This element has a key, right? So they give you an element, you do a get key on the element because all the elements must implement the get key interface, right? And the key is what you are going to use to hash. Okay, so you do an e dot get key dot hash code. Okay, that is the hashing function that you are going to use. Okay, in order to figure out which bucket it's going to go into. Okay, so once you get the element, when somebody says insert this element into the table, the element itself is going to have to be a keyed element. So it has a get key function. You get the key, you get the hash code for it. That gives you a number, okay? And then you have to modulo it, okay, by n.
What is hash code in this case?
Hash code is a given function. Every object, if you look at the object class in Java,
Okay.
the object class has a bunch of methods in it that are well defined. One of them is toString, okay? One of them is equals, okay? And one of them is hash code.
So this is something that is included in Java. Okay.
That's already defined in Java.
Okay.
Every object implements this hash code, whether it implements it itself or it inherits it from object. Okay? It's going to return to you a hash code, and then you have to modulo it with n in order to get inside this hash table. Okay?
Okay.
And let's, for argument's sake, say that the first element hashed to bucket number 3. Okay? Which means this is nothing but a linked list, right? The linked list has, I don't know, what do they call it? Head and tail, right? So really, the bucket really has a head and a tail. So now you add a node in here, a doubly linked list, element number 1, right? Is it doubly linked list or a singly? I think it's a singly linked list.
Singular.
So element number one, and then there's nothing else, and the tail points to it, right? That's what the linked list will do for you, right? Another element hashes into bucket number 5. So I get the head and the tail. So here we go. I have another element over here, element 2, and then there's nothing else in it, right?
What about if it hashes to 3 again?
So now if you hash to 3, you go to that linked list and you say at entry 3, you go to that linked list and you say add this element to the list, right? It is a linked list. It knows how to add to itself, right? So element number 3 will go over here, right? And now the tail points somewhere else, right?
Also, and this list only we only have the things pointing to the next. We don't point to the previous.
I don't think so. I don't think our homework is requiring us to point to the previous.
Yeah, because it's not
a doubly linked list. Are we okay so far? So now, as I add things into this table, okay, they're going to go into one of these linked lists, okay? And eventually you're going to have elements that are sitting all over the table, right? Head, tail. I have another element over here, element number 4, okay? I add another element to number 5 over here. I have another element over here, element number 5, right? And so you're going to end up essentially what your hash table is going to look like is exactly like this. Okay, your buckets, which are these here, these are your buckets. Okay, you're going to find out which bucket it goes into, and you go to that list and you say add this element to your list. Okay, and so that's what your hash table is going to look like. So what about this do we need to discuss, Eric? Do you have any particular questions about this beyond this?
So for what I'm seeing, so then the head is the first element that was introduced, right?
Mm-hmm.
Okay, and so
until somebody says remove that element from the list, right?
Okay.
Because we have a remove function, right? And if somebody says remove element number 1, you know, giving us the key to the element, then I will just remove element number 1 from the list, and that becomes the list, right?
Okay, perfect.
So it's a list. Each one of them is a list. It behaves like a linked list, like we did before. Okay? And you should be able to manipulate each list individually because each one of them is a separate list, right? The list at index 0, the list at index 1, the list at index 2, and index 3, so on and so forth. Okay? And now you have functions in there to find out, you know, what is the size of this hash table? How many elements are in this hash table? Well, you can either keep track of that yourself, or every time somebody asks, you can go through all of these lists and find out what the size of every list is and then sum them up and return that result, right? Because that's how many items are in your hash table.
Yes.
Okay.
Yes.
Is that good? Does that answer your question, Eric?
Yes, that answers your question.
Anybody, do you have any other questions?
If no one have any other question, I do have another question.
Well, okay, let's give somebody a chance to ask. Anybody else has started on working on the homework? Because I can tell that Eric has gotten started because he has specific questions.
All right, so I have probably referred to your question. I don't know, it was something that would either be handled over office hours, but I think it'd be good for everybody. There's with the hash table, I know you gave us a hint on the private fields for one of the you gave us a hint for one of the private fields for the hash table class.
Mm-hmm.
The one that has to do with like person, integer. I kind of just want to make sure like that I have that field right. So then, you know, at least that doesn't hold me up from.
Which field are you having? Do you have a question about?
The buckets. It's a field called buckets.
Yeah.
Yeah, no, I just wanted to like kind of make sure that like the where it has because because it would have two reference objects, E and K, but then for some reason that didn't work. So, and looking at the hint, it showed person, comma, integer again. I don't know if you know what I'm talking about, but in the hint, you mentioned something like that. So I kind of wanted to make sure like I had my private field was correct for buckets. I don't know.
Okay, let me just take a look over here to see what, which field, so the buckets field is the one that you're having a hard time with? That you
Yeah,
know,
yeah.
okay. Uh-huh. And what do you need to know about that?
So yeah, like in terms of I guess the how it says linked list, I had at E comma K, and I don't know if
Yeah, linked list E comma K buckets. That's what the hash table, that's what the constructor looks like in your hash table. Okay. But when you call it, when you're actually going to call it, you're actually going to pass in something that looks like what it is that is in the assignment. Okay. Because you're going to pass in a person integer. Okay. The element is the person. Okay. So every element E in all of these classes, let's write this in a different color. Okay. So we can see it better. E. Okay. And E, you also need a K. Okay. E is the element and K is the key. Okay. Now the element needs to implement the keyed interface. Okay. So person, in our case, implements the keyed interface, which has a get key. And the person element, so person is a generic class. Okay. And when we create person ourselves, we create person with an integer. Okay. Which means that the key is going to be an integer. The key is integer. In other words, when I want to create a hash table, the hash table, I create a hash table with a person, integer, and integer. Okay? Because the hash table has two arguments, two generic parameters, the element and the key. When you define your table, you're defining it in terms of E and K. But when you're using it in terms of P, person, integer, and integer. Okay? Do you follow what I'm saying?
so far.
Okay. So that when you define your hash table, it will be defined just like the hash table interface is defined with E and K. Okay? And when you define your constructor, it's going to be E and K also. But when you call the constructor, okay, you define the constructor by saying hash table, and it takes two parameters, E and K, right? Those are the two parameters it takes.
Yeah.
And then, but when you call it with a person integer and an integer, because that's the specific type of hash table that you're creating. Okay? All right? Anybody else?
Yeah, quick question. So every element in the array for a hash table, so every element in the array for a bucket is of type linked list, right?
Yes, every element in the buckets list is a list itself, right?
Okay, great. Thank you.
It's an array of lists. Yeah. Eric, you said you had another question?
Yes, a quick question about the constructor and the constructor we have to do in the hash table. The constructor say that we have to clone the buckets. Is clone a function that we define somewhere, or
No, clone is defined for you. Okay, that's another function that's defined in object.
because I was trying to use it and it was giving me like an error.
Clone?
Yeah, I was saying like add a cast, like to fix it. We had like I had to cast it or something.
Uh, I don't have that problem.
Okay, so I can discuss it with you in office hours and then.
Yeah, so discuss it with me in office hours. Let's see.
Okay, thank you,
Okay.
thank you.
Uh-huh. Okay, anybody else? All right, let's get going with this assignment because we only have until Sunday to finish it. Okay? It's an interesting assignment. Let's get going with that. What else? Is there any other questions about, if you have a specific question about your progress report, feel free to contact me through a private message on Slack. If you want to talk to me about it, feel free to schedule some office hours time for us to talk. And if there are corrections to be made, you can either private message me about the correction that needs to be made, or you can email me back. Email me about the correction that needs to be made. Okay? And if we need to talk, then I'll say, let's schedule some time to talk. Otherwise, I'll just make the correction if it is one of my errors that I had that I made, which I'm very capable of. Okay? What else? All right, so if they're barring any other questions, I'll give another minute or two for questions if anybody has a question, and then we'll jump into going back into binary trees that we were talking about. Okay, because today we're going to spend time about binary search trees. Okay, like how do we put things into the binary search tree and how do we find things in a binary search tree? Okay, and so we're going to spend today and probably most of the next class as well talking about the binary search tree and how we create it. And your next assignment is going to be built on top of this binary search tree that we're going to create together here. Okay, so going once, going twice, 3 times, if there are any questions. Otherwise, we'll get started. Okay. So what I'm going to do this time is I'm going to share my screen, but I'm going to share my Eclipse as well as I'm just going to share the whole screen. You should be able to see my Eclipse and my both of them together, right? So, so what we're going to do here is we're going to work on creating our own binary search tree. Okay. So when we were talking about the binary search tree the other day, remember I told you that every starting at the root, okay, if I remember, these are all nodes and they contain values in them and pointers, right? Because a node could have 2 children, right? So that's a node with an element in it, and it's got a left child and a right child. So we're going to create all of that. But the thing that I'm most interested in is how do I put things into a search tree? Okay, because when I get things to put into the search tree, I want to be able to go to the search tree and say, here, put this element in the search tree. Okay, if my elements are given to me in some random order, excuse me 1 second, I think it sounds like, ooh, I thought I was going to sneeze. If my elements are given to me in some random order, okay, so let's say somebody gives me the number 15 to put into the tree and there's nothing in my tree yet. So the number 15 becomes the root, okay? If the next element, so the elements that we're gonna get are gonna be 15, 10, 20, 40, 5, let's start with those, okay? So 15 has been put into the tree. 10 is the next element that I want to put into the tree. Well, 10 is less than 15. So it has to be to the left of 15. I look to the left of 15 and oh, I did have to sneeze. Sorry. 10 is smaller than 15. So 10 is going to fit as a left child of 15. There's no left child to 15. Okay, so I'm going to put 10 over here. It's going to be a left child of 15. When I get to the 20, 20 is bigger than 15, so I'm going to put it over here. Okay, and 40 comes to me, and then now 40 is bigger than 15, right? So I go down to the right. There is a right child to 15, so I can't put it there. I look at it and compare it to 40, and 40 looks like it's bigger than 20, so it'll fit over here, right? But the number 5, when 5 comes, 50, it's less than 15. So I go down to the 10 and I look at the 10, and it's less than 10, so the 5 will go over here. Now, if I'm going to insert the number 12, 12 is less than 15. So I go down here, I'm looking at the 10, it's greater than 10, so it's going to have to go down here. That's 12. And if I get the number 18 to put into the table, I'll look at 15, it's greater than 15. The right child of 15 is 20. It's less than 20, and the 20 does not have a left child, so 18 goes over here. All right? So this is how we want to insert things into the tree, okay? By comparing it as we are traveling down the tree as we're going, okay? And we're going to start always at the root, looking at what's contained in the root, and compare the element that I'm trying to add to the element that is in the node, and then I'll decide, do I need to go left or do I need to go right? Okay, so this is how we insert things. Now, the order of insertion is important, okay, because if you're not really paying attention and you are unlucky to get your data in numerical order or in reverse numerical order, for example, if I end up with the numbers, these same numbers here, and I have them sorted, when I'm putting them in 5, 10, 12, 15, 18, 20, and 40, what happens to my tree if I'm going to insert them in that manner? Well, 5 is the first one, so it becomes the root. 10 is bigger than 5, so it's going to go over here. 12 is bigger than 5, and it's also bigger than 10, so it's going to go here. 15 is bigger than 5, bigger than 10, bigger than 12, so 15 is going to go here. 18 is going to end up going here. 20 is going to go here. And 40 is going to go there. That got a little bit cramped over there. Let's see if we can fix that. So that's 40. So you can see that my tree is no longer a tree. Okay, I mean, it is a tree, but it's not what we call a balanced tree. Okay, it looks like it's a skewed tree. It kind of looks more like a list than a tree, to tell you the truth, because we don't have the benefit of having all the elements close together like they are in this situation over here. All right, so when we enter data into a tree, how we enter the data into the tree, especially if the data is sorted, is very important, okay? So if we know in advance that the data that we're gonna enter into the tree is sorted, we will talk later on about how to insert this into a tree in order to obtain a tree that is a well-balanced, what we call a well-balanced tree, and we're gonna define that term balanced, okay? Because what I'm saying is that this tree on top, this tree over here, is a well-balanced tree. This one is not a well-balanced tree, okay? So we wanna aim to preserve the balance of a tree because it gives us the most performance as far as being able to access the data. If I wanna access the data in this not balanced tree down here, it's gonna be, balancing the data is gonna be very similar to going through a linked list. Is essentially is order n to find an element if it is not a balanced tree like this. But if it is a balanced tree like it is up on top, it's going to be order of log n, log base 2 of n, okay? Which is a much smaller number than n, okay? So it's very important for us to preserve the balance of a tree in order to benefit from the lookup speed that a balanced tree gives us to finding elements. But we're going to come to that later on. I just wanted to discuss this insertion thing because that's the next thing we're going to do. Okay? We're going to create a tree and we want to insert things into the tree. Okay? So why don't we go ahead and start a project to do just that. Okay? So what we're going to do is we're going to create a project that does a binary search tree. And so I assume you can see my Eclipse over here. So we're going to create a new project, a new Java project. And that new Java project, we're going to call it binary search.
Professor, I have a question. Sorry for interrupting.
No problem. There's no interruptions here.
Yes. So I guess my question was, so we would prefer a balanced tree rather than a screwed tree, right?
Yes.
So does that mean we want the list unsorted since it makes the balanced tree?
That is actually a good question. If you don't mind holding on to that question for a day or two.
Oh, okay.
Okay, we are going to come back to this.
Oh, okay.
Okay, we are going to come back to the balance issue. Okay, I'll give you a sneak peek. Okay, if I was to, if you, this is the data that we have over here. Okay, if I was to do an insertion of this data in the sorted order, instead of doing it in sorted order, if I do a binary search, okay, where, you know, you search for the middle element, you insert that first, okay? And then you go to the left-hand side, you find the middle element, you insert it next, okay? So the middle element of the tree is 15 of this list. If I insert the middle element first, 15 becomes the root. If I go to the left-hand side of that and I pick 10, 10 is going to be the middle element of the left-hand side. That's going to be the left child of 15. 20 will be the right child of 15. 5 will be the left child of 10. 12 will be the right child of 5, 10. 18 will be the left child of 20. 40 will become the right child, which is exactly what we have above. But the order in which I inserted it was slightly different. Okay? But we're going to talk much more about this later on. We're going to talk about balance and height and all this other stuff. That's going to be part of your assignment for this. And we're going to go over the algorithms for how to do all of that together. Okay?
Okay, thank you.
Sure. So let's go back to our binary search tree here. We created a project. And what we're going to do is we want to create this new class called binary search tree. Okay, and really, so the binary search tree that we want to create can take a bunch of elements. Okay, and so the way we did the elements as keyed elements in the hash table. I showed you how to do that. Today we're going to look at the binary search tree, and the binary search tree is going to have two parameters. Okay, two generic parameters, a key and a value. Okay, so instead of the element, okay, being an element that contains a key, here the binary search tree is going to think of the element and the key as separate things. They might come from the same place, but the tree is going to think of them as separate. Okay, but the key in this case needs to be a comparable element, just like we did earlier when we were let me just move my iPad so I can type. So the key must be a comparable element, okay? So it must extends comparable, or like very much like we did with the linked lists before, okay. or either it extends comparable or a super class of the key compare has, so they must implement the comparable interface. So these are the tree is going to look like that. Okay, it's going to contain key and a value. Okay, so the key must be comparable, so that's why we express it in this way. Okay, so the tree is going to consist of a bunch of tree nodes. Okay, they're going to have nodes. So let's define the class that is the node class for the tree. Okay, new Java class, and we're going to call this a tree node as opposed to the other nodes that we were doing. Okay, so the tree node also contains a key and a value, right? It contains a key and a value, K and V, right? But the key extends comparable, or some super of K extends comparable. Okay, so that's what the node has, the same thing as what the tree has. Okay, so what are the elements in the tree, right? I mean, the tree node contains the following items, right? It contains so the tree node contains the tree node has a few things in it, right? It has the elements, the value that we want, right? And it has a left child, and a right child, right? Anything else that it has? So the other thing that the node also has is it knows who its parent is. Okay, so every node has a value, okay, and it contains, it knows who its left child is, who its right child is, and who its parent is. So when I look at a tree like this, like 20 over here, 15 will be its left child, but 15 will also have a pointer at who its parent is. Okay, so every node knows who its parent is, and every node knows who its children are. Okay, so there's a parent pointer in every node. So let's put that in here. There's a few fields in here. So so the things that we're going to put into here are tree items. Okay, and what is a tree item? Okay, a tree item contains two things. Let's create that tree item, because that's the thing that we're going to put into the tree. Those are the items, the elements that we're going to put into the tree. Tree item, okay? And the tree item itself consists of a key and a value, right? A key, which extends comparable, or some super of K, and it contains a value also, okay? And so what are the things in here? So private K key and private V value, right? That's what's in here. And when I construct when I create a constructor using the fields, create a constructor using all fields. It creates me a constructor that takes a key and a value. Okay, we don't have a super here, so we don't need to worry about it. Okay, the object is not necessary for us to call it super function. Okay, we want getters and setters for all of these. Set the key. Let's get to the setters and the getters and setters for all of these functions. Source, getters and setters. Okay, we want all of them for now, and we might delete some of them if we want. Okay, so get key, get value, set value. Okay, get key, get value, set value. Okay, what else do we need? We need let's do the toString method, so that we have a toString method to do that. Source, toString. Okay, create a toString method. There we go. We have a toString method for our item. So whenever I want to put something into the tree, it's going to have to be one of these items. Okay, I create the item. I give it the key and I give it the value and it goes in here together. That's the items that I'm going to be able to put into the tree. Okay. So any questions on the tree item so far? There's nothing more to the tree item. This is it. Okay. We don't need anything else to do with the tree item. This is what with the tree item that we are going to work with is going to be. So going back to our tree node. So the tree node is clearly, okay. So what is a tree node going to have? It's going to have a tree item. Okay. A tree node contains a tree item. So private tree item, KV, tree item, okay? That's the item that's in the node, right? That's the value, which contains the key and the value in it, okay? Then we have a left child, okay? So private tree node, KV, okay? Left child, okay? Private tree node, KV, is the right child. And private tree node, KV, parent. Okay, we know the left child, we know the right child, and we know who our parent is. Okay, and so we can create the basic constructor that we're going to need in here. So public tree nodes. It takes a tree item, KV, tree item. So when we create an item, we put it in here. So this dot tree item is equal to tree item, okay? And this dot left child is equal to null, just to make sure everything is initialized properly, okay? This dot right child is equal to null, and this dot parent is equal to null as well. So that's the initializer, okay? Get tree item, set tree item. We want the getters and the setters, right, for all of these methods. So let's do that. Let's do getters and setters. We want getters and setters, and Eclipse is really good at that. So we want to be able to get and set all of these, and do the getters and setters. Get the item, set the tree item, get the left child, set the left child, get left child, set left child, set left child, get right child, get set child, get set parent, so on and so forth. So we have all the getters and setters, okay? And the last thing we need is as a construct is a toString. So let's do the toString for this. Source, create a toString for that. Yeah, that creates a toString. And let's leave it at that. Maybe we'll fix it later on and come up with a better one. Okay. All right. We'll fix that later on if we need a better toString. I think we might. But so these are the basics. We have. So what do we have so far? We have the binary search tree. We have an error in here. What did I do? All right, so I hadn't saved the binary search item. All right, so we have a node, we have an item, okay? Those are all good, and we have a binary search tree, and the binary search tree doesn't have anything in it at all yet, right? We didn't do anything in the binary search tree. So, but we know what are the nodes and what are the items that we're gonna use, and now we gotta create our binary search tree. So what do we need in a binary search tree? Okay? The thing that we need the most in a binary search tree, like when we had the list, what did we do in the list? Okay, when we had a list, what did we do? In a list, we had a pointer to the head and a pointer to the tail, right? So when I added something to the list, I point the head and the tail to it, and now I know where my list is, right? I could, so this is what I have in a list. When I had a queue, I needed to know the front and the back, right? In a stack, we need to know the top of the stack. Where is the top of the stack, right? So for a binary search tree, the tree is structured like this, right? When I add things to the tree, it looks like that. The only thing that I need to know is who is my root. I only need to know where my root is at, because once I know where my root is, then I can find the rest of the stuff in the tree. So the only thing I need to keep track of in my binary search tree is my root. So private tree node KV the root. That's it. That's all I need to keep track of my binary tree. Okay, that's the only variable that I need to keep track of my binary search tree. So now I can create a constructor. Okay, let's create a constructor. Let's create a constructor from the fields. Okay, that's one that takes a root if I specify it, or I can create a constructor that doesn't take anything, okay, and sets up my root to null. Okay, so what does it do here? That root is equal to null, right? That's all I need here. These are the only two methods that I need for the constructor. I either create an empty root, a tree with nothing in it. I can do that if I call the default constructor. Or if I have already a root that I want to create the tree with, I can say, here's a new root. Now you have the tree starting at that root. Okay. It'll be nice to have a getter for the root. Okay. And it'll be nice to have a setter for the root. Okay. That's another thing that we will know. So generate getters and setters for the field root. Now we have a getter and a setter. That's really cool. You know, it'll be nice to have an is empty. So public Boolean is empty, which basically returns return this that root is equal to null. If the root is equal to null, then the tree is empty. Okay? If the root is equal to null, then the tree is empty. All right? So far, so good. Any questions about the binary search tree so far? We haven't done much with it yet, but we're setting up the infrastructure for building our binary search tree. Okay? So let's continue, because we have more stuff. We have a lot more stuff to do here. So one of the items is that, well, if I have a root, I'd like to find out what is in that root. I don't know why I want to find out, but let's do it. Okay? So public it returns an item, right? Because we have items that we put in our tree, and the items are of type KV, right? Get root item. Okay, get me whatever item happens to be in the root. Okay, so we can say return this dot root dot get the item, get the tree item. Okay, that would be cool. But what if my root is null? What if my root is empty? There is nothing in my root. Then I will have, if I do this, then I will end up with a null pointer exception here. Okay? And that's something that you guys got to pay attention to when you're writing your code, because whenever you reference an object, like this object over here, root is an object. It's a node. It's a tree node. Well, if that is null, then that since the root is null, then when it goes to try to get the tree item from that null item, it's going to say null pointer exception. I can't do that. Okay, so we need to guard against that. So let's guard against it, and we say if this dot root is equal to null, then we want to throw an exception saying you can't get what is here. Okay, so what we're going to create is we're going to create an object which is a tree exception. Okay, we might use it a few times. So let's create new class. Okay, we're going to call it tree exception. Okay, and the tree exception is a very simple little exception. All it does is it extends runtime exception, and it'll return a message. Okay, the tree exception extends runtime exception. Okay, and all it is it got a constructor public tree exception string message. It has a message, and it just calls super, which is the runtime exception, and it passes in the message that you gave it. Okay, that's all that is in the tree exception. It's just a way of us putting a message into it so that you can get it back. Okay, and we say that this method over here, binary search tree get root item, can throw, throws a tree exception. Okay, and if the root is null, then I want to throw that tree exception. Okay, so throw new tree exception, and the message should be something to the effect that, sorry, tree exception, binary search tree is empty, no tree item available in the root. No tree item available. That's good enough. Okay. Else, we're going to return what we want. Okay. So that's the get the tree item. Okay. So let's do this. So now we have the basics. So now the only thing that's missing is for us to be able to add things into this tree. Okay. So what we're going to do is we're going to create a method for insert. Okay. So public void insert, and when somebody goes to insert, they're going to pass us a tree item. They say insert this tree item into this tree item. Okay. Okay, that's what they're going to do. When they call us to do this, they're going to call us to insert this particular item into the tree. It's going to be a tree item that we're going to try to put into the tree. So let's call it a tree item. All right. So I'm going to define these methods up here, the public methods, but there's going to be a bunch of private methods that we're going to call underneath to do the work for us. Okay. We're going to keep the public methods to be very simple, and we're going to make the private methods do the hard work. Okay. So these are my private methods. And okay, the private methods. So what we're going to do here is we're going to create a private method that's going to do the work, and insert is going to call it private void insert insert item. That's the name of the method. And they're going to pass in the tree item that's going to need to be inserted. Okay. You're going to see why we do this because the insert method turns messy pretty quickly. It'll be nice to hide that as a private method down below that does it. So when somebody passes me something, I'm going to say this dot insert item, okay, and pass the tree item to whoever needs to insert it, okay. And then what we're going to pass to that method is, in addition to the tree item that was passed to us, we're going to pass in the root, okay, this dot root, okay, to that method, okay. And do we need to pass in anything else? Let me just double check to make sure that I'm not forgetting something. I need to also pass in the parent, okay? I need to also pass in the parent of this. So the parent of this, the root node is null. There is no parent, okay? We'll see why we need that later on, okay? We will see why we need that later on. We're not gonna see it like right away. So insert item, it takes a tree item, it takes a tree node, KV, that's the root, okay? And it takes a tree node, KV, and that's the parent. And it takes a tree item to insert the method, okay? So how do we do that? How do we do this? Well, we're going to do this two different ways. Today, we're going to do it by writing code that has a while loop. So it is a looping piece of code. Eventually, we're going to learn how to do this recursively. Trees lend themselves to recursion a lot. And we're going to explore those properties of trees as we go. Okay? But first, we're going to insert this item non-recursively. Okay? And how do we do that? Okay, so, well, we are in this method here. And we want to insert something into the tree. Okay, so let's do that. So I have an item that I want to put into the tree. Okay, and I want to put that starting with the root, right? So this is what I'm going to do. So the first thing that I'm going to do is I'm going to create a new node and put the item in it, just like we did with lists and queues and stacks and so on and so forth. So I'm going to create a tree node, which is of type KV, okay? The new node is going to be equal to new tree node, KV, and it's going to take in the tree item that was just given to me. So create a new node to put the thing in here, okay? And then I'm going to ask the question, if my root is empty, okay? If my root is empty, okay, then I'm just going to set that to be my root, my root, okay? If the root is empty, okay, if root is equal to null, there is no root here, okay? So I'm going to make root is equal to the new node, right? And root dot set parent is going to be the parent, okay? That's it. That's all we need to do. That means I am starting with an empty tree, okay? I'm starting with an empty tree. There was nothing in my tree. And now I have set this new item to be my root. This is the first element that I have put into the tree. It has no parent, it has no children. It's a root all by itself. There's nothing else in that root, okay? But what if the root is not empty? Else, If the root is not empty, that means I want to find the place to put it into the tree, right? Okay. Otherwise, I want to find where to put it in the tree, correct? So let's try that. Let's do this. So I'm going to start with the current node. So I'm going to create a tree node, KP, current node. Let's call it current node, not current node, is equal to the root, right? Starting at the root. While current node not equal to null, right? Because presumably the root is not null at this point. We checked for the null case above. Okay, while the current node is not equal to null, okay, I want to now figure out, I am going to look at my root and I want to figure out this new item that I'm inserting. If I have element number 1 in my tree already, and I'm adding another element. So somebody gave me, so element number 1 was that 20 that we put into the table, into our tree. So 20 has been put into the tree. Now I want to put 15. Okay, so somebody gives me 15. I got to be able to compare this 15 to the element that is in the table, that is in the root. If it's smaller than it, then I want to go to the left, right? I want to go to the left. So if it's bigger than it or equal to it, I'm going to go to the right. So what I want to do here is I want to compare the key of the item that I have in my hand, this tree item that I want to put in. I want to compare the key, okay? Compare keys. So we're going to write a method to compare keys, okay? We're going to write a method to compare keys. And the method to compare keys is very simple. It's a compare. So let's write a method down here, compare keys. Okay, we're going to make that because we're going to use this a few times here. So might as well write it once. So nope, that's not what I want. We want to create another method over here, private integer, int, it returns an int, compare keys. And the keys are that I'm using are a key, K1, and a key, K2, 2 keys that I'm going to compare. Okay. Remember, in the compare to method, if K1 is greater than K2, I want to returns a positive number. K1 is equal to K2, returns 0, and K1 is less than K2, it returns a negative number. That's what the compare to method does. And now all I do is return K1 dot compare to K2. Okay, that does all of that for me. Okay, so that's the method compare keys. There's nothing else to it. It just does a comparison of the 2 keys and then returns to you a number. Okay, so in our insert method over here, wherever we were, right here, I want to in my insert item up here, I want to now compare the key that I have to the key that is in the current node. So I'm going to say if, so since I'm inserting here, I'm sorry, I got to keep track of where I am in the code. So this is not the kind of code that I remember off the top of my head. So I need my handy dandy cheat sheet. So if this, well, I want to compare that compare keys okay? And the two keys that I want to compare is the current node that get tree item that get its key, right? Because the tree item, remember, has a method that says get key, right? So we want to get the key from it, and I want to compare it to the tree item which is K2 over here, the one that the tree item that I'm inserting. I'm going to say the tree item that get key, okay? And I'm going to ask the question, okay, is this number greater than 0? If this number is greater than 0, it means that the tree item that get key the tree item key is less than cur node dot key which means go left. So I have the 15. The 15 is the key, and I'm going to compare it to the 20. 15 is less than 20, so it means I want to go left. Okay. Okay. So else I want to go. Else, what we have is a tree item. The tree item that key is greater than or equal to cur node that key, which means we want to go right. Okay, so if we want to go left, we're going to look at going left from here. Okay, so if we're going left, okay, that means I'm going to look at the current node. Okay, so I am in this state here. I have 15 in my hand, which is the new node. So the new node is 15. Okay, that's 15. And I want to put it as I'm going to try to go left from 20 and go down there. Okay, so I'm going to look and see if the left child of the current node is null. Okay, if the left child of the current node is null, then that's very simple. I just got to make it its child and make it point to its parent, and that's it. So let's ask the question. If cur node dot get left child is equal to null, that means I found where I want to put it. It's going to be the left child of the current node. Okay, so the cur node dot set left child is equal to the new node. Okay, okay, and new node dot set parent is equal to the cur node. Okay, and we're done. So in our case, this is where we're going to be here. We're inserting the 15. I looked at the 20. The 20 was not null. So I came into this code right here, and I looked at the 15 and said 15 was less than the item in the current node is bigger than the item in the tree in the item that I'm trying to insert. So therefore, I want to go to the left. And therefore, I look at the left child of the current node, 20. 20 is null. It doesn't have a left child. So I say, okay, if it doesn't have a left child, make it the left child. So 20 now has a left child. Okay? And the left child has a parent. And the left child has a parent, which is 20. Okay? And we're done. Okay? There's nothing else to do here. Otherwise, else, okay, get the left child, okay, cur node is equal to cur node dot get left child. Okay, we're going to see where that becomes useful now in a second. Okay, so now I want to insert 5. I want to insert, 5. So what happens? I come into this code over here and I look and I say, is the root null? No, it's not. Okay, well then continue. And the tree node, current node is this one. I'm going to keep track of the current node that way. Okay, this is my current node. Okay, and I'm going to ask the question. Let's move that a little over so we can see it. So I'm going to ask the question now, is the current node, get the current node, which is equal to the root, okay? And keep going from here, all right? If the current node is not equal to null, the current node is not equal to null. So let's keep going. I'm going to ask if this key 5 is less than the key that is in this node, the current node. Yes, it is. So I want to go left. So I go left. If the current node has a left child, yes, it has a left child. So I'm not doing this code. I'm going to go down to this code. I'm going to say current node is equal to current node that get left child. So now the current node is 15. And I will loop again. Because remember, I'm in a while loop here, right? So when I loop back again, the current node is not equal to null. So I will go down through here. So now 15 is my current node. And I say, is this not 5 less than 15? And the answer to that question is yes. And it says, is the left child of 15 null? And the left child of 15 is null. So I'm going to go ahead and insert it then over here. So I have a new node that has the 5 in it. Okay. And this becomes the left child of 15, and the 5 has a parent of 15. So now the node has been inserted into the tree and I'm done. So if somebody gives me a 10 to insert, okay, or like let's take a different number. Let's take a 17, okay? 17 is gonna be less than 20, okay? So this while loop is going to go down over here. We're going to go down left, right? And then we're going to go and look at the 15, and then we're going to compare it to 17, and 17 is going to be bigger. So which means that it's going to be the right child of 15, but we haven't written the code for the right side. It's going to be very similar to the code on the left side. So it's going to say if cur node that get a right child is equal to null, then make this the right child, okay? Then cur node that set right child equal to the new node, right? New node that set parent is the cur node, and then return. Otherwise, else, cur node is equal to cur node get right child. Otherwise, go to the right, okay? And that really is it as far as the insertion is concerned. That is really it as far as the insertion is concerned. There's nothing else to it, okay? Let's verify that that's the case, okay, by walking through this code. We're inserting 17 now. I look and the node, the root is not null, okay? I come down here and now I'm in the while loop. The current node is not null because the current node is the root. So let's make that the current node. That's current node, okay? And now I compared the key 17 to 20. 17 is less than, so we're going to go to the left. So the current node is, then I look at and see if the current node has a left child. Does the current node have a left child? Yes, it does. So I make the current node the left child. And then I go back and then I go back in the while loop and I come back. I compare the 17 to the 15. The current node is bigger. 17 is bigger than 15. So I come down here. I say, does 15 have a right child? No, it does not have a right child. Well, very good. Then take the new node, 17. Okay, make it the right child of 15 and make its parent that. And then that's it. 17 has been inserted into the table. If I get 25, I want to put 25 into the table. Well, 25 is bigger than 20. So I will fall through and compare the keys. It's going to be bigger or equal to 20. So we're going to come here. We're going to say, does it have a right child? Yes, it does. No, it does not. Right. 20 does not have a right child. So make 25 over here and make it the parent, right? Make 20 the parent. We're good so far? So this is how we insert things into the tree. This is the logic in a non-recursive manner. We're going to come back to this and look at this in a recursive manner, probably on Monday next week. Okay? Any questions about the insertion?
Yeah, I have a quick question. So yeah, I understand that the compare keys, I got a bit lost, but I understand that the compare keys is you're comparing the first key with the second key.
Right.
And the compare to, yeah, that if K1 is greater than K2, then you get a positive and return 0 and the negative. So I understand those because you wrote that here.
Okay.
The part that I get a bit lost. So the root is always considered to be the current node is always considered to be the root.
We start at the root. We always start at the root. Okay.
Okay, because I think I get a bit lost once we get like to the if statement after the while loop. Like, so right when we hit the while condition and we go into this if statement, that's where I get a bit shaky. Like I'm trying to get lost.
So say that again one more time, Johnny.
No, I'm saying I get lost. I got a bit lost once we got into the while loop. Like once we went through the while loop condition. I guess going into the if statement after the while loop, that's where I got lost.
Okay, so we know that we're comparing two keys in this compare key, right? One key is the item that is in the current node.
Yeah.
And the other one is the key of the item that we are trying to insert. So K1, okay, K1 is the item that is the key of the item that is in the current node.
Okay.
And K2 is the key of the item that we're trying to insert right now.
Okay.
So K1 and K2 are those. Okay. So
Yeah.
I'm saying if K1 is less than, so in other words, if the key that I'm inserting, if K2 is less than K1, I'm going to go to the left. If K2 is bigger than K1, then I'm going to go to the right. Okay? If K2 is bigger than or equal to K1, I'm going to go to the right. If K1 is bigger than K2, I'm going to go to the left. Okay? That's the only thing that we're doing here. Think of this here as being key 1, K1, which is the one that is in the current node. And this is the one that I'm trying to insert. So I'm comparing two different keys. Okay? Look at this piece of code later. You'll understand it a little bit better by if you just pay attention to what the K1 and the K2 are. Okay? That's all.
Yeah.
I'm comparing key 1 to key 2.
I think that's what it is. But I mean, it makes a little bit more sense. Yeah, I definitely have to look at it a little bit more, but it makes a bit more sense. A little bit more sense.
Okay.
Professor?
Yes.
Yeah, at first I thought this was really confusing, but then I took a step back and like looking at this while loop, you can see like it's just mirrored, like it's literally the same thing in the first, if section in the else section.
Mhm.
Like you just change left and right.
Right, exactly. They're exactly mirror images of each other, right? If I'm going right, I'm going right. If I'm inserting it on the right, I'm inserting on the right. If I'm going left, I go left. Otherwise, I insert it on the left, right? They're both exactly mirror images of each other. And if you think of the while loop as just basically navigating the tree. So now let's get the number that I want to insert now is going to be 23. Okay, let's go through this, okay, for 23. All right, where is my current node? I start out with my current node being up here, right? 20. Correct? And I look at that number and so I'm comparing K2 is 23 and K1 is 20. Well, 23 is bigger than 20, right? So I'm going to go to the right. So if I'm going to go to the right, I'm going to be down here, right? If I'm going right, I'm going down here. So I look at the current node and I say, does it have a right child? Well, the current node 20 has a right child. So if it has a right child, make the current node the current right child. So now the current node moves down here to 25. Okay? And now we loop back up in the while loop. Is the current node null? No, it's not. Okay, well then go down. Compare. The two keys that I'm comparing, this key, the first key is the current node get item get key. That's the 25. Comparing it to 23. Well, 25 is bigger than 23. So 3 is going to be to the left of 25. So I come down here. Does 25 have a left child? No, it does not. Well, that's very good then. Put it over here. 23. Make that the left child and make it the parent, and that's it. 23 has been inserted. When I get the number 30 that I'm going to put in, well, we start again at the root, and root says 30 is bigger than 20. So I come down here. I look, does it have a right child? Yes, it has a right child. It is 25. So go back up. Compare 25 to 30. Well, 30 is bigger, so I come down here. 25 does not have a right child, so I will put 30 over here. Okay? So that's essentially how that works. And that's how we build our tree, one node at a time as we're inserting things into the tree. Okay? Does that answer the questions about how this is being done? This is actually a pretty straightforward operation. Okay? It turns out that for now, okay, we do not need those parent and node and so on and so forth, but let's remove them from here. We don't really need them. Okay, we don't need those. Okay, whoops. Let's go up here and remove that. The insert, we're just inserting the element, the tree item itself. Okay, and the code in here, if this dot root is equal to null, okay, this dot root is equal to the new node, and this dot root dot parent set parent to null. There's no parents. Okay, so that's how we're doing this right now. Okay. Later on, when we do the recursion, we're going to need this other stuff, but we don't need that right now. Okay? So, any questions about this method? Any other questions? I'm going to post this so you guys can take a look at it, and we're going to process. We're going to go through more of this stuff as we go on. Okay, but I'm going to post this code so you can take a look at it yourself. Between now and Monday and be a little bit more comfortable with what we have done so far. Okay? Any other questions on this? Let's take a little break and take attendance. About the attendance, when I sent the progress report, some people were alarmed about the fact that the attendance was in the progress report. And I had people asking questions. Oh my God, I didn't know that your syllabus says nothing about attendance. Attendance is not something that figures into your grade, so please don't worry about it. I just do it for my own knowledge. And the only time I use attendance, and I really mean that, the only real time that I use attendance is if at the end of the semester, your grade is in between two grades, okay? It's like in between a B plus and an A minus, okay? It's like really close. And I can't decide whether it's a B plus or an A minus. Well, attendance will figure out in making that decision for me. I'll look at the attendance, and if your attendance was good, it'll probably be an A minus. And if your attendance was not good, it'll end up being a B plus. That's the only time that your attendance will count. And
Okay, which is not bad.
Which is not
Because
bad.
yeah, okay. Thank you, Professor.
Which is not bad. I like to give people the benefit of the doubt. I know this is a crazy time and we're all at home and have a million things that we need to do and keep track of, but and you can always watch the videos later on. So I'm not gonna punish you because you don't attend the class live, but I want to reward those who did come to class just a teeny little bit, okay? And most people don't end up having a grade like that. I mean, in all the years that I've been teaching, I've had to use this maybe a couple of times, okay? Usually I give people the benefit of the doubt and they'll get the A minus in that case, okay? So we have another method that we need to write, which is the find method. It's gonna take a little bit longer than 10 minutes, so we're not gonna do that today. We'll do that on Monday, okay? And then we'll just keep adding to this binary search tree a little bit at a time. Binary search tree is a really interesting class. So we're gonna data structure. So we're gonna spend some quality time in class writing the code for it and doing all the fun things that we need to do with it. Okay. So we're gonna stop at this point. Any questions before we stop? Okay, so everybody have a good weekend. Good luck on finishing homework number 5. And I'll see you back over here on Monday. And then we will pick up from here, from where we left off today to work on this assignment. Okay? Actually, come to think of it, we're not going to be ready to start this assignment, the binary search tree, until sometime later in the week. So your assignment next week is due on Tuesday, right? It's not due on Sunday. So you have a couple of days into next week to finish this assignment. So you're going to see me again on Monday, and we have office hours Monday and Tuesday, and we can resolve whatever problems remain as we go forward. Okay, so have a good weekend, and I'll see you back over here on Monday.
Thank you, Professor. Have a good weekend.
You too. Bye-bye.